I'd like to end lecture number 9 with a few final thoughts of what we've covered in this lecture. First off, let's summarize some of the major steps that we'll use when solving a finite element problem using a method based on the principle of minimum potential energy. The first thing you want to do is you want to find a function for the total potential energy stored in your system as a function of the unknown displacements you're trying to solve for. Once you have that function, it's time to move on to step number 2. And what you're going to do is try to find the minimum of that function with respect to your unknown displacements. You'll do that by taking the partial derivatives of that function with respect to those unknown displacements and setting those partial derivatives equal to 0, similar to what you did when you tried to find the minimum of a function in your first calculus course. When you've done that, if you have n unknown displacements, you'll now have n equations with n unknowns, those unknowns being your unknown displacements. You can write this linear algebra system of n equations and n unknowns as a matrix vector problem, and then you solve for that matrix vector problem similarly to what we did when using the direct method. Now, I'd also like to point out an advantage to using the method of minimum potential energy. And that is, we never had to apply boundary conditions to our problem. That step is removed. Why? Because the application of the boundary conditions was baked into our derivation of the minimum potential energy method. Finally, I'd like to discuss a little bit more about what we're actually doing when we use this method. Now, suppose I have a bar, and I've applied some forces to this bar. And because I've applied forces to the bar, this bar has stretched to some extent. So this node I'll call node number 1, and this node I call node number 2, has both displaced by some amount u1 and u2. Now, in reality, this bar has, every point in this bar has been displaced by some amount, and I have some function of my displacement as a function of x, where this function has meaning anywhere in the x direction along this bar. There's potential energy stored in this bar because this bar has been stretched. So there's strain energy and potential energy stored in this bar now that these forces have been applied. So there is some function, potential energy, and that the total potential energy stored in this bar is actually a function of the function of my displacements. Okay? Now, if I wanted to graph this function u of x, supposing I knew the displacement at u1 and I knew the displacement at u2, I could write that as, or graph that if this was my displacement at u1 and this was my displacement at u2, I could plot this graph. Now, in this particular case, this function u of x turns out to be a straight line. It only turned out to be a straight line because this bar has a constant cross-sectional area and the bar has a constant Young's modulus. But it also turned out to be a straight line because of all the possible displacements and all the possible displacement functions I could have. This is the only function which minimizes this function, the function of my total potential energy in the system. There are other possible displacement functions, and these functions are perfectly valid for the displacement, but they don't minimize my total potential energy in the system. So to summarize, what I'm saying is we can think of this method of the principle of minimum potential energy method as a way, can be thought of as finding the function u of x that minimizes the function total potential energy in my bar, which happens to be a function of u of x. Now, I went over that fairly quickly, and I know that's a lot to take in. We'll discuss this more in lecture number 10, and we'll also start applying principal and minimum potential energy methods to bar elements that we could not, and trusses that we could not solve using the direct method.